Any general questions, problems, anything? I'm also monitoring the chat if anybody out there has questions. Quick reminder, again, if you got my email, I'm pushing the OWL back a week. Essentially, Sprint 2 is going to be 3 weeks long because we're about a day behind and there's really no point in rushing to get caught up just to get the OWL homework done. And there is sort of an extra week in the schedule anyway, so it'll just make everybody's life easier. And of course, Project 1 is due this week, so. Any other issues, anything? Okay, well, we got to this problem and didn't get to solve it, so here it is again. And again, the kinetics section of this course, or maybe I should be less course conscious and just say kinetics in general, tends to be highly experimental in the sense that you can't really tell by just looking at the reaction what the kinetics should be. And for us, that mostly means rate law, right? Ultimately, the descriptor, the most general descriptor of the kinetics for the reaction is the rate law. And so rate laws have to be experimentally constructed. And so the experiment looks something like this, right? Where I'm measuring the rate, right? Which could be done by measuring the change in concentration of anything in the reaction, right? Typically, it's a question of what's easiest to measure, right? And it's something that has to sort of be measured on the fly in the sense that, right, if I can't measure it while the reaction's going on, if I have to do something else to measure it, right, it becomes tricky to know exactly what the concentration is. It's sometimes possible to quench the reaction, stop it, and measure things. But most of the time, right, I adopt some methodology that allows me to measure it as the reaction's going. And a lot of times that's spectroscopic. I mean, in lab, you use the UV vis spectrometers. If you have something in this reaction that has a clear absorbance signature in the spectrometer, you can just run this whole reaction in the cuvette in the spectrometer and watch the absorbance of light change as the reaction occurs, right? There are other fun tricks to do this, but ultimately, for this final data, I don't really know which one of those four things was measured. I don't need to, right? I might have measured the change of ammonium, but again, I always report my rates as the more generic rate of reaction rather than the more specific rate of change of ammonium. Right. And because the rate is not constant, right, I try to take short slivers of rate measurements at the very beginning of the reaction, which is why it's termed initial rate, right? And so that's the rate at which the reaction starts, right? I don't really have all the experimental details here, not that I need them, right? I don't know if that measurement was done for 1 second or 1 year, right? Depends on how fast the reaction is as to whether I would measure it for 1 second or 1 year, right? But ultimately, right, my unit is always some version of moles per some unit of time. In this case, because this is an aqueous reaction, it's molarity per second. Right. And so again, as we mentioned at the very end of class on Friday, right, I know what the rate law should look like, right, before I even do anything. right? It's got to depend on one or both of the reactants, and it's going to depend on the one or both of the reactants to some order, some power. Right? And so essentially, if I'm going to construct the rate law, and this is generically true for all reactions, I always need one more piece of data than I have reactants, right? Because I always need, if I'm going to construct the rate law, to figure out what those two orders are. And of course, I also need to know what K is, right? The rates and the concentrations are the measurable and the initial conditions. And so those I know in the context of the experiment, but there's always one more thing I don't know than I have reactants. And so there's three things I don't know. And so I need to do, in this case, 3 experiments to do it, right? And you can see what I did if you look specifically at the difference between the experiments. If you look at experiment 1 and 2, right, I kept the ammonium constant. I kept the temperature constant, which means K is not changing, and the ammonium contribution to the rate is not changing. And so the only thing that changed was the nitrite, right? And so effectively, by my choice of initial conditions, right, still 298 Kelvin, still 0.1 molar ammonium, any measured change in rate has to be due to the nitrite and only the nitrite. And so I've isolated one of the variables I needed to know. All right, similarly but differently, right, if you look at the second and third reactions, there I kept the nitrite constant, as well as, of course, the temperature. So again, the only thing that changed now is the ammonium, and so any change in the rate has to be due to the ammonium. And so quite frankly, especially because I made up this data, and so it is a very exact difference, right? I can actually construct the rate law just by looking at it, right? When I doubled the nitrite concentration, comparing experiment 1 to experiment 2, right? I doubled the nitrite, the rate exactly doubled, right? And so that is a strictly linear dependence, right? I got exactly the same change in rate as I had concentration. In other words, the order of the reaction had to be first, right? If I look at the second and third reaction, I did the same thing only with ammonium. I doubled it, and again, the rate doubled. And so, quite frankly, I already know it's first order in ammonium and it's first order in nitrite. Right? I also know, having done this for a number of years, that some of you hate that. And not just because it's new. Some people always hate that. Right? And so I don't really have to do it just by looking at it. I can do the math, right? But I'm going to start again with my generic expression for the rate law, and I'm just trying to, one at a time, determine what my 3 unknowns are. The rate constant, the order with respect to ammonium, and the order with respect to nitrite. And so what I'm really going to do is write the rate law for each of my experiments, right, using the values I have, right? Symbolically, I've called it, rate 1, meaning experiment number 1, right? But for all of these, right, I have a rate and I have the initial concentrations of ammonium and nitrate. And so I can construct an equation that has 3 unknowns in it. right? And if you're big fans of algebra, or at least moderately competent in algebra, right? If I construct three equations with three unknowns, it's solvable, right? And the way I'm going to solve it is by reducing, right, the three unknowns to one unknown at a time. And I can do that by, again, my judicious choice of experiments, right? If I look at experiment 1 and 2, there's only one thing that I changed, right? Which was the nitrite concentration, and the rate changed as a result of that. And so what that means is a whole lot of things cancel if I use the two rate laws for those two experiments. All right, right off the bat, since they're all at 298 kelvins, the rate constant's going to be the same no matter what the orders of the reaction are, no matter what the concentrations are. And so they will cancel. And so essentially, again, I want to use my word compare, which always means either subtract or divide. In this case, dividing is most helpful in terms of getting cancellations. And so I write the two separate rate laws for the two separate experiments, and I divide one by the other. And so right off the bat, the K's cancel. Again, please note, the K's cancel because the temperatures are the same, right? If this was, 350 degrees instead of 298, the K's would be expected to be different because K is temperature dependent. But as long as I held the temperature constant, the K's cancel. I still have two unknowns, X and Y, right? But again, because the ammonium concentration was the same in both cases, right? When I plug in the values from the experiment, no matter what X is, 0.1 to the X is going to cancel 0.1 to the X. And so there was a method to my experimental madness. I intentionally picked values for concentration that allowed this cancellation to occur, right? And so very conveniently, I end up with one equation with one unknown, and therefore I can solve for Y. Yes, no, maybe. Algebraically, I don't want to bore you with more algebra talk unless you're confused by the prior algebra talk, in which case I will risk boring you to illuminate you. Okay, so I'm down to one equation with one unknown. Sadly, right, the unknown is the exponent. So that is not perhaps the most common algebraic problem you solve, right? But it is solvable, right? I can simplify a little bit, right? A number to a power divided by a number to the same power is actually the number divided by the number to the power, meaning 0.005 to the y divided by 0.01 to the y is actually 0.005 divided by 0.01 to the y, right? The rates are just a ratio, so that's just a number, right? And so if I do the math, I get 0.5 equals 0.5 to the y, and so pretty clearly y has to be 1. Right. Again, it partly is clear because I faked the data, and so it very exactly was double the concentration and double the rate. In practice, it might not be quite so exact, but right, because of what the order means in the context of the reaction mechanism, my bias is for integer orders. Right. And so I'm kind of looking for integers or half integers because they do represent the stoichiometry of the mechanism. If I want an exact number, and it didn't work out quite that exactly, it is solvable using logs, right? if you want to get something out of the exponent, which is what you'd need to do to solve this equation, right? The solution is the log, because I remind you of a log property, right? The log of a number to a power is the power times the log of the number, right? In other words, the log of 0.5 to the y is y times the log of 0.5, right? That gets the y out of the exponent and puts it in line with the other numbers, although my other numbers are now logs, but hey, log of a number is still just a number. All right, so again, basic algebra, if I want the equality to remain, I have to do the same thing to both sides. So I take the log of both sides. That gives me log of 0.5 on the left-hand side, and it gives me y times the log of 0.5 on the right-hand side. And so y ends up just being the ratio of those two logs. When you go to the internet, and clearly you will, because many of you found the wrong answer key on the internet for the spring synthesis. 1 foot is not 30 inches, folks. 1 foot is 30 centimeters, but somewhere out there, I've seen it before, there's a wrong answer somewhere on the internet and people find it, right? If you go on the internet, it'll give you all kinds of fancy algebraic relationships for this, because what you really have there is the order is the log of the rate divided by the log of the concentrations. And so you can find sort of prepackaged algebraic solutions to this. I'm not necessarily a big fan of prepackaged algebraic solutions because you can always just do the algebra, but they're out there, right? The orders of the reaction always ends up being a ratio of the log. Can I go back one slide? There. Well, you have to tell me something. How long am I supposed to stay on this slide, and what's the question? You too can own a set of these slides available on my courses to you, right? And so that little piece of math eliminates one of my unknowns. I know the order with respect to nitrate has to be a 1. Right? I still have 2 unknowns, but that's okay. I still have more data, right? And I can find X similarly by now using experiment 2 and 3, right? Because again, in 2 and 3 now, the only thing concentration-wise I changed was the ammonium. And so frankly, the nitrite is irrelevant between those 2 experiments. Even if the nitrite is different at this point, it doesn't really matter because I know the order, right? And so I'm going to do the same thing again. I write the rate law for experiment 2, I write the rate law for experiment 3, and I compare, meaning divide the 2 rate laws. And again, I get all kinds of useful cancellations. The K's cancel. This time the nitrite cancels, although again, as I said, technically I know these are 1s, so it doesn't really matter if they do cancel, but it's just a number, right? And once again, I get a ratio equal to a ratio to a power. Right, and once again, the ratio is 0.5. Right. And so I'm 2/3 of the way done, right? My rate law is first order in ammonium and first order in nitrite. Right. The only thing left to determine is the rate constant. Right. Again, the rate constant is temperature dependent. Since this whole experiment was done at the same temperature, I can find K at that temperature. Because in fact, at this point, I actually have 3 separate measurements of K. Right? Since I know the orders of the reaction, I know everything except K for all 3 of my experiments. I have the initial concentrations of both reactants. I have the measured rate. I know the orders. The only thing I don't know is K. Right. Again, from an experimental standpoint, I really should take the average of all three, since I do have three. In this case, because I made up the data, they end up being identical. More identical than they would be in an actual experiment, of course, because there's going to be some fluctuation due to experimental error, right? But at this point, again, I'm just plugging in the data for my experiment, so I know the rate for experiment 1 and the 2 initial concentrations, both to the first power. The only thing to solve for is K, and so I do. Right, and again, because it's totally made up data, too perfectly made up so there's no experimental error in it. Right. I get exactly the same K for all three. Right. And so the average K is also 2.7 times 10 to the minus 4. And I have essentially the rate law at 298 Kelvin. Right. Again, the one limitation on my rate law here is because K is temperature dependent, I don't get a completely generic result for K quite yet. Right, and so the only thing I know is the specific K at that specific temperature. If I change the temperature to 350 kelvins, right, I'm going to need a different K value. Right. As we mentioned on Friday, though, the good news is the orders, right, should stay the same no matter what the temperature is. Right. So the only thing I really need to address temperature-wise is the K dependence on temperature. Yes, no? Maybe. That is known as the method of initial rates for somewhat obvious reasons. Right. And it is the most common way to determine the rate law. There is another way which we'll look at on Wednesday. Right. In terms of the temperature dependence of K, really I just need one more experiment, right? Since the orders of reaction stay the same, if I suddenly was at 350 Kelvin, it just means I have to run an experiment at 350 kelvins, and then I could calculate the rate constant at 350 kelvins by, again, just plugging in the concentrations and the rates. Right. That said, there is a way to generalize the temperature dependence of K. Right. And so if I really want the most generic description of rate that I want, right, knowing the orders of the reaction lets me mostly get the rate law. If I also then determine the temperature dependence of K, I have by far the most generic result. And so I will, based on what is the most common theory for the temperature dependence of the rate constant, and that goes back to our first but not our last look at what is I often call the most important diagram in all of general chemistry. Right. All reactions progress in energy through a pathway that looks something like this. Right. The specific height of the hump varies. Frankly, whether delta H is positive or negative varies. Right. It's also possible to have an exothermic reaction as well as an endothermic reaction. But in fact, all reactions progress through a journey something like that. My reactants have some cumulative total internal energy, which we generally refer to as enthalpy. Enthalpy is just energy measured under certain conditions. The products also have some total internal energy, call it enthalpy, which is different than the reactants, right? And so either the products are higher in energy than the reactants, right, as in the case of my actual drawing, in which case this is what's known as an endothermic reaction, or the products are lower in energy, in which case it's an exothermic reaction. All right. And so for an endothermic reaction, it's absorbing energy. For an exothermic reaction, it's releasing energy. Right. The exothermic or endothermic part is the energy part you feel, right? Because that's the net result of the reaction. You know, it starts out at some energy and it ends up either hotter or colder, and you feel the difference. All right. That is not, however, the hard part for the reaction itself. The hard part is the part you don't feel, but the molecules do, right? And that's the journey to the top of the hump, right? And generally speaking, that hump is much bigger than any of the energy difference between the reaction and the products. It is the biggest energy term in my diagram, right? It is the hardest thing my molecules have to do if they're going to react, right? And this is frequently referred to as the activation barrier. Where EA is the activation energy. And as I say, we keep coming back to this diagram because it is critically important. It does describe, right, the general energy pathway for a reaction, right? And, you know, depends on whether you want your, you know, glass to be half full or half empty here, right? Either the activation energy is the hard part, right? Or if I want to think in terms of the stability of the universe, the activation energy is a useful way of stabilizing materials, right? If you remove the activation barrier, reactants and products are constantly sliding back and forth into each other because there's no real barrier to doing so, right? I keep walking back and forth across the front of the room for those of you at home who just see a blank screen, right? Put a hill in the middle, I'm going to stay on one side. Right. If I make the trip over, I'm likely to stay on the other side once I get there. And that's really what the activation barrier allows to happen. My reactants tend to stay stably as reactants, only gradually working their way over to products. And once they're on the product side, they will tend to stay products and only gradually working their way back.
I have a quick question.
Yep.
Would the x coordinate, like on the bottom, would that be just like time?
No. The question was, is the x-axis time? No. The time parameter is very, very different depending on the reaction. Reaction coordinate really refers to essentially a reduced dimensional minimum energy pathway. If I really wanted to draw this the way the reaction actually happens, I need to have a multiple dimensional graph, because not every molecule has exactly the same orientation and the same energy. And so this thing is really a multidimensional surface that the molecules are traveling around, right? And reaction coordinate is the minimum energy pathway, or it's the positional minimum energy pathway, but it doesn't directly correlate to time. In fact, time is really more on the y-axis because it's the activation energy that's going to correlate to the time. The bigger the activation energy is, the harder it is to get over.
So the x-axis right now, it's like kind of like how far the reaction is carried out. You know, it's like
What do you mean, the x-axis?
Yeah, would it just be like the duration of like how far the reaction is completed?
No, again, you're still trying to make it into time, right? In fact, at any time, you're somewhere on that surface, right? And so, you know, pick your favorite time, right? You're here. At that same time, a different molecule's here, right? At the same time, a different molecule's here. right? That whole thing is one split second in time, right? Because again, remember, I don't have just one molecule that's doing this. That's why I say it's really a cross section of a multidimensional surface. I've got, a mole's worth of molecules, each of which has slightly different energy and slightly different orientation, is in a slightly different place on that surface, right? And so that's really the pathway in energy for for a single molecule at a time, right? But for all molecules on average.
I have a question.
Yes.
Is activation energy consumed in the reaction?
Well, yes and no, right? I mean, to go from here to here requires that I absorb energy, but I get most of it back on my way down here, which is why the only thing I feel is the delta H.
I guess what I'm trying to say is if the delta H is 0, does that mean that their reactants and products will just keep switching between each other?
No, there's still an activation barrier.
Well, like if it gets all that energy back, then wouldn't it just have the energy to absorb again?
But you're talking about two different things, right? So I'm in Gosnell. I don't know where you are, but whatever building you're in, there's two sides of the building, right? Presumably. So on the east side of the building, you could be standing there. And assuming you're not on one of our hillier buildings, the other side of the building is at exactly the same altitude, right? But your only way to go from one side to the other is to climb over the building, right? So are you going to tell me that all day long you're going to be flopping back and forth between sides of the building? No, because even though you get energy out on your way down, you have to put a whole lot in to get over it in the first place. Right? There's a big difference between the net energy, which again is the delta H. Even if the delta H is 0, you still have to climb over a mountain to get back to 0. It's easier to stay on the side you're on. You follow me?
I'm just a little bit confused because like if it has the activation energy, like if you heat it up enough or give it activation energy in some way, maybe a catalyst, I don't know, then it would react, right?
Okay, first of all, remove catalyst. Second of all, would it react? In a very random, long journey, it doesn't choose to go over the hill. It doesn't know what's on the other side of the hill. It gets to the hill, top of the hill by random collisions with other molecules, many of which actually lower the energy and move you back down. So if you're trying to get over the hill, you go up a step, you go down a step. You go up 2 steps, you go down a step. You go up another step, you go down 2 steps. Eventually, if you're fortunate, you get to the top. Once you're at the top, your next step, 50% of the time, is to slide back down where you started from. It is a tortured path to do the reaction. Now, if you had 0 activation energy, you would slide back and forth between products and reactants because there would be no barrier to do so. I mean, think of it this way. You want to make $100?
Sure.
Apparently not. Sure. Give me $1 million. I will give you $1,100,000 back. The offer stands for 10 seconds. Right? Even if you win on delta H, you still got to pony up the $1 million up front. Right? That is a barrier to doing it. Right? Even if you had 100 in the back, because again, you're looking at it as though you know what the whole journey looks like. The molecule does not. It's at one point in space. It doesn't know where it's going next. It doesn't choose. It just keeps bumping into things. And so that activation energy, regardless of what's on either side of the barrier, is a huge hurdle for the molecule to overcome. I mean, potentially huge, obviously. Activation energies can be giant or small. But that is the hard part for any reaction. I have to climb my way to the top of the hill just to get a 50% chance to slide down into the right side. right? And when I'm up there or down in either valley, I really don't know what's on the other side of the hill. And so, again, the only net energy you feel is the delta H. You either end up higher in energy or lower in energy. But when I say you, I mean you personally, not you, the molecule. You, the molecule, is just you, the molecule. You end up where you end up. You don't know that you used to be lower or higher in energy, right? And so you don't choose to go over the barrier because it's better for you on the other side. You just end up on the other side of the barrier because you randomly bumped your way over there.
Professor?
Yes.
I have a question. So, what exactly is forming this barrier? Like, what does the activation energy go into? And, like, why is there a barrier there?
Well, there, again, depends on the molecule. There's bonds that need to be broken, right? There's orientations that need to be established, right? At the very least, if you're doing a reaction, you're making or breaking a bond, right? Somewhere at the top of the activation energy, which is sometimes referred to as the transition state, you sometimes have highly strained bonds that are ready to break. For example, the energy went into creating that arrangement where you had highly strained bonds that are ready to break. Once they break and reform, you get most of that energy back, or sometimes more than that energy back if it's exothermic.
Okay, thank you.
Right. Now, again, to get to the top of the hill is a tortured, collision-filled journey. And so it only makes sense, right, that it is easier to get to the top of the hill if I have more frequent high energy collisions, right? Because the more colliding I do, the more energy transfer there is, the more likely it is I'm going up in energy, right? And the bigger the whack in that collision, the bigger the step up the hill. And so if you combine those two things, you end up with what's known as the Arrhenius equation. This is very common, not even just in chemistry. It applies to other things like glue drying, right? Anytime there's an activated process with a barrier, right, there is some version of the Arrhenius equation. So, you know, they may change the variables on you, but you'll see some version of this in physics and biology. There's all kinds of processes which obey an Arrhenius type relationship. In our particular case, right, what you really have is a trade-off among three things, all of which I previously mentioned. My activation energy is the thing I need to overcome, right? Again, it's the hard part of my journey from products to reactants, right? That energy comes from collisions. And so the two parameters that help supply me that energy are temperature, because again, temperature is the median kinetic energy. The higher the temperature, the bigger the whack when I collide, right? And the number of collisions. And so the A, which is sometimes called the Arrhenius constant and other times called the collision frequency factor, right, is really a system parameter related to the cross section of the molecules and the frequency of collisions, right? And so my collision frequency coupled with my temperature gives me enough energy to get over the hurdle, right? As is frequently the case, there's multiple ways I could express this same relationship, right? This again is the more classic way that Arrhenius formulated it. Of course, experimentally, whoops, we're all about straight lines, right? I can actually reformulate that so it looks like a straight line. If I take the log of both sides, right, and do a little algebra, right, I get what is essentially a straight line relationship between, again, I always have, which is my independent variable, the thing I have a knob for, which in this case, again, is just temperature, turn up the heat, and then my dependent variable, which is the thing that changes in response to it, which again, in this case, is the rate constant, which was the whole point in this exercise, right? My rate constant changes when the temperature changes. How much depends on my constants in here, right? There's R, our kind of universal gas constant. So that's our old friend. And then you have the two reaction specific system parameters, which is the activation energy, right? And the collision frequency factor, right? And so again, what I have here is a recipe for measuring those if I'm so inclined, right? If I want to know the activation energy and the collision frequency factor for a reaction, right? Measure the rate constant for a bunch of different temperature and make this graph. The y-intercept is the natural log of my collision frequency factor, and the slope of my line is the activation energy over R, the gas constant, which I already know. Right. And so, in fact, in that form, I have a perfectly good way of actually doing the experiment, right? Much as when we were doing Clausius-Clapeyron, if you'll note, it's a similar looking relationship, right? As it would be, because even though Clausius-Clapeyron is talking about pressure, right? Pressure is force per unit area. It is the kissing cousin. Happy Valentine's Day. It's always been a strange expression to me, kissing cousin, but it is the kissing cousin, right? To energy. It's force, not energy, but force acting over distance is energy, right? And so it's not a big surprise that they have functionally similar form, right? In the case of Clausius-Clapeyron, it depends on delta H and the Clausius factor. In this case, it depends on the activation energy and the Arrhenius constant, but it's really a similar dynamic. What's what? Rate constant. Right. And so I can also do a similar trick to what we did with Clausius-Clapeyron, which is to essentially construct the 2-point straight line. Right. And so I do exactly what I did with Clausius-Clapeyron. I won't belabor the point here. I write an Arrhenius expression for one temperature, right? I write an Arrhenius expression for a different temperature, and I quote unquote compare them, by which I mean, again, divide. And I get, again, what looks like perhaps a slightly more complicated expression, but it's really essentially just a 2-point graph, so it saves me the graphing problem, right? And it gives me a way to determine the activation energy if I measure the rate constant at 2 different temperatures. And frankly, I've already seen how to measure the rate constant at a temperature. As long as I know the orders of the reaction, measure the rate at the temperature, right? And so, in fact, I don't really need a really complicated graph to address my temperature dependence of K, right? All I really need is one more data point than I had a minute ago. I don't know, there's a practice problem there for no reason, right? Which is, where is it? Here we go, right? If I wanted the most generic version of the rate law, right? I really just need one more data point than I had before, right? Which is I need one other temperature, right? And so again, here I've got a reaction that has 2 reactants, right? Right off the bat, to get the rate law, that means I need 3 equations, right, at the same temperature. If I want to then add the temperature dependence, all I need is one more measurement at a different temperature. And so the bottom experiment is now at 550 kelvins instead of 500 kelvins. Right. That gives me my 2 data points to use my 2-point Arrhenius equation. Right. Which gives me the activation energy, which would then allow me to calculate the Arrhenius factor. And then I have the most generic expression for rate I could possibly have, which has not only the orders of the reaction in it, but also the temperature dependent expression for K, right? And so we can do that. We'll try it 4 minutes. We'll do the shorthand version of the orders, right? Again, I did, the usual sort of useful construction of the experiment. If I look at the first 2 data points, I kept the oxygen the same, right? I doubled the amount of hydrogen, right? When I doubled the amount of hydrogen from the second experiment to the first experiment, the rate approximately doubled. I built in a little experimental error here. And so the order of the reaction with respect to hydrogen should be 1. So it's first order in hydrogen because doubling it doubled it. Now for all the fun and cash prizes, right? If I look at the second and third, now the hydrogen was constant. If I doubled the oxygen, the rate increased by a little more than a factor of 7. That makes the order third, right? Because again, it's 2 to the what power, right? If it's first order, it's 2 to the first power, so the rate should double. If it were second order, it would be 2 to the second power. The rate would go up by a factor of 4. If it's third order, it's 2 to the third power, which would be a factor of about 8. Maybe I built in a little too much experimental error there, right? And so, again, if you don't like that method, and some people never do, and there's no reason why you have to do it, you can always go through and calculate it by dividing the rate laws and using the logs. But I'm trying to get to the K part of this, and so I took the shortcut, right? And so the rate law should be third order in oxygen, first order in hydrogen, right? And now I just have the K issue, right? If I was doing everything at 1 temperature, I only need the 1 K. If I want to be truly, truly generic so that I'm not tied to that single temperature, what I want is the Arrhenius expression for the K, because that's what Arrhenius tells me is the temperature dependence of K. And I do have 2 different sets of temperatures, right? I have the 500 kelvins data, right? Those should all have the same rate constant. Again, I both did you a favor and I cursed you by building in some experimental error here, right? But if I take those first 3 experiments that were all at 500 kelvins, the K should be the same. The fact that they're not is simply the experimental variation. And so again, if I've got all the data, I might as well use all the data. And so the average rate constant at 500 Kelvin is 1.39. We probably should say something about units, but we don't have time. We'll say something about units on Wednesday. But if you crunch the units there, you get reciprocal atmospheres cubed in reciprocal seconds. Right. I only have 1 measurement at 550 kelvins. If I really, really, really want to do a good job, maybe I want to do multiple measurements at 550 kelvins. Right. but I do have one measurement at 550 Kelvin. And so again, if I plug in the data for that experiment at 550 Kelvin, I get what should be a different K and is. Right? And that's all I really need are those two K values to determine the activation energy. Right? If I use my 2-point Arrhenius equation, the K at 500 Kelvin, the average K was 1.39. The units are going to cancel, so I left them off. At 550 Kelvins, right, the K value is 1.59. R is R. Again, if I want my energy to be in joules, I want my R to be in joules. And I'll sort of leave you there and pick up with it, I think, on Wednesday, because I don't want to keep you that long. Right? Once I have the activation energy, I could use this expression at any temperature I want. Right? If you want it at 400 Kelvin, just plug it in. Or I could calculate the A value, which gives me the K expression as a function, and I have by far the most generic expression for K. But we'll pick it up with that on Wednesday. Again, don't forget the project. If you have questions, pop into office hours or try to email me. Otherwise, happy President's Day. One holiday after another this week.
Professor,
Yes.
just a quick question. When you were talking about the finding the order, you said it was 2 to the something power. Why was 2 the base there when you were looking at that?